Hey there, science fans. Today we're diving into the fascinating world of data structures and algorithms. Now, these might sound like complicated computer science terms, but trust me, they're not as scary as they sound. Imagine you have a big box of Legos. You can use these Legos to build all sorts of awesome things like spaceships, castles, or even robots. In the world of computers, data structures are like those Legos. They're the building blocks we use to organize and store information. Algorithms, on the other hand, are like the instruction manuals that tell us how to put those Legos together. They're sets of steps that we can follow to manipulate data in specific ways, like sorting it, searching for something specific, or even just storing it in the first place. Understanding data structures and algorithms is like having the ultimate Lego building toolkit. It lets you create efficient and elegant solutions to all sorts of problems. So buckle up, because we're about to embark on an exciting journey into the world of data structures and algorithms. Linear data structures are like a straight line of Lego blocks. Each block follows the one before it in a specific order. One example of a linear data structure is an array. An array is like a train with a fixed number of cars. Each car can hold a piece of data, and we can access each car by its position in the train. Imagine each car has a number on it, starting from 0. The first car is car number 0, the second is car number 1, and so on. Another example of a linear data structure is a linked list. A linked list is like a chain of paperclips. Each paperclip represents a piece of data, and each paperclip is linked to the next one in the chain. Unlike an array, a linked list can grow or shrink as needed. You can just add or remove paperclips from the chain. Linear data structures are great for storing and accessing data sequentially. They're like the assembly line of the data structure world. Now imagine if our Lego creations weren't limited to straight lines. What if we could build them in all sorts of crazy shapes and structures? That's where non-linear data structures come in. Non-linear data structures are like branching trees or interconnected webs. The data isn't stored in a simple, straight line. Instead, it's organized in a more complex way, with elements connected to each other in various ways. Think of a family tree. You have grandparents at the top, then parents below them, and then children branching out from each parent. This hierarchical structure is a perfect example of a non-linear data structure called a tree. Another example is a graph, which is like a network of roads connecting different cities. Each city is a piece of data, and the roads represent the connections between them. Graphs are super useful for things like mapping and social networks. Non-linear data structures give us more flexibility in how we organize data, which is super helpful for solving complex problems. Let's take a closer look at two fundamental data structures, arrays and linked lists. Both are used for storing collections of data, but they have some key differences. Arrays are like neatly organized rows of lockers. Each locker has an address, and we can quickly access any locker if we know its address. This makes arrays great for storing and retrieving data quickly, especially when we know the index of the data we're looking for. Linked lists, on the other hand, are like a treasure hunt. Each piece of data is like a clue that points us to the next one. This makes linked lists more dynamic than arrays. We can easily insert or delete elements anywhere in the list without having to move everything around. Think of adding a new locker to the middle of a row. You'd have to move all the lockers after it. But with a linked list, you just change the pointers, which is like changing the clues in our treasure hunt. The choice between an array and a linked list depends on the specific needs of our program. It's all about finding the right tool for the job. Section 5, Stacks and Queues, first in, first out, and last in, first out. Stacks and queues are like special kinds of lists that follow specific rules for adding and removing elements. They're like the bouncers of the data structure world, controlling how data enters and leaves. Imagine a stack of plates. You can only add a new plate to the top of the stack, and you can only remove a plate from the top as well. This is called last in, first out, or LIFO. A queue, on the other hand, is like a line at a ticket booth. The first person in line is the first person to get a ticket. This is called first in, first out, or FIFO. Stacks are used in all sorts of applications, like tracking function calls in a program or undoing actions in a text editor. Queues are great for managing tasks that need to be completed in a specific order, like printing documents or processing network requests. Section 6. Trees, Hierarchical data organization. Trees are hierarchical data structures that are perfect for representing data that has a natural parent-child relationship. Like a family tree, a tree data structure has a root node at the top, and each node can have 0 or more child nodes. Think of a file system on your computer. The root directory is like the root node of the tree, and each folder within it is like a child node. Each of those folders can contain more folders or child nodes or files, which are leaf nodes. Trees are used in various applications, such as organizing data in databases, representing the structure of a document, or even building efficient search algorithms. One specific type of tree, called a binary search tree, is especially useful for searching because it organizes data in a way that allows us to quickly find what we're looking for. Section 7. Graphs, networks of relationships. Graphs are like maps of interconnected data points. They consist of nodes, which represent entities, and edges, which represent relationships between those entities. For example, in a social network, each person would be a node, and a friendship between two people would be an edge. Graphs are incredibly versatile and can represent a wide range of relationships, from social connections to transportation routes to the flow of information in a computer network. Algorithms that operate on graphs can help us answer questions like, what's the shortest path between two cities? Who are the most influential people in a social network? How can we optimize the flow of traffic in a city? Section 8. Key algorithms, sorting and searching. Algorithms are the engines that power our data structures. They provide us with the instructions to manipulate and process data stored in those structures. Two fundamental algorithms are sorting and searching. Sorting algorithms allow us to arrange data in a specific order, such as alphabetical order or numerical order. This makes it easier to find information and analyze patterns. Searching algorithms help us locate specific pieces of data within a larger data set. Imagine trying to find a specific book in a library without an organized system. It would take forever. Searching algorithms provide efficient ways to find what we're looking for. There are many different sorting and searching algorithms, each with its own strengths and weaknesses depending on the specific data and the desired outcome. Section 9. Real-world applications, from maps to social media. Data structures and algorithms are everywhere in our digital world, even if we don't always realize it. They're the hidden heroes behind many of the technologies we use every day. Mapping applications rely on graphs and shortest path algorithms to find the fastest route from point A to point B. Social media platforms use graphs to represent social connections and recommend new friends or content. Search engines use sophisticated algorithms to index billions of web pages and return the most relevant results for our searches. Video games use data structures and algorithms to create realistic physics, artificial intelligence, and immersive virtual worlds. Understanding data structures and algorithms gives us a glimpse into the inner workings of these technologies and allows us to appreciate the ingenuity behind them. Section 10. Conclusion: the importance of data structures and algorithms. Data structures and algorithms are the fundamental building blocks of computer science. They provide us with the tools and techniques to organize, process, and manipulate information effectively. By understanding different data structures and algorithms, we can choose the most efficient ways to solve problems and develop innovative solutions, whether we're building software applications, analyzing data, or simply trying to understand the technologies we interact with every day. Knowledge of data structures and algorithms is essential, so keep exploring, keep learning, and keep building. The world of data structures and algorithms is vast and fascinating, and there's always something new to discover.